Hello and welcome to the show. My name's Relevant. This is Do All the Things. On today's episode, Beep, or as I sometimes call him, Mew. This is my take on a classic prank. Now, I'm not gonna lie, this isn't an original idea. It was actually inspired by AVE Zen Blaster, where he takes an Arduino and he programs it to let out like a chirp noise at random intervals and whatnot. Well, it needed a speaker and it needed an audio amplifier and it needed more power supply than he wanted to design it with. And in my opinion, it's actually pretty complicated for how simple it's intended to be. And I got to thinking, how would I do that? Using my design methodology and what I know about circuits, how would I make something like that? Well, this is what I came up with. And the wonderful thing about it is it's completely mechanical, electromechanical. No coding, no fancy circuitry. It's something that anyone can build, even if you don't know a thing about Arduino, and it's a lot more power supply flexible. So see here, we have a circuit with options. I have a timing option here, and right now it's thinking. It's thinking. And at some point, because I'm not gonna wait for it to do this, when it is done doing what it does, it lets out a little, which is one reason why I call it Mew. It's actually got a cute little sound to it, like mew. Maybe not quite as annoying, but it's going to accomplish the same goal. In this timing setting right here, I believe it's gonna be roughly 9 to 10 minutes before it goes off. But if I flick it up, you're gonna be waiting an hour, which is perfect for that long game prank stoosh it around somewhere. So, how does it work? Very frickin' simple, but actually, it is just a classic relaxed oscillator using a Schmidt trigger inverter. So see it here, we got a 9-volt input. This is powered off a 9-volt battery to keep things real simple. And to work with this 9-volt battery, we use a slightly different part. It's called a Toshiba TC4S584 if you punch that part number into DigiKey or Mauser. It is what I consider a high voltage logic circuit. You see, most of the logic circuits I might use to build something like this, the 74 series, HC, LVC, even the LS, they're designed to run off like 5-6 volts max. You hook them up to a 9-volt battery, they're gonna fry. The TC4 has an absolute maximum rating of 20 volts. With an average of up to 18. So it's designed to work with common higher voltage circuits, 15, 18 volts, 12 volts, etc. So it has no problem working with a 9-volt battery, which means we need no voltage regulation to make this thing work. Quite simply, we have ourselves a capacitor here. When you very first turn this thing on, it defaults high, and we have a quick shoot of high signal pass through this 4148 diode and through this more smaller resistor. And what happens is that's going to charge up this capacitor. Once that capacitor is charged up, the input goes high, the output goes low. This diode blocks any further interaction with the capacitor, and then it's forced to use the larger capacitor, RT, our timing, RD is our duty. I'll explain that more later. So what will happen is this capacitor is going to slowly discharge through this resistor, because if you know how logic works, the output is active. It's either high or low, which means that output's basically getting directly connected to either the positive pin or the negative pin. So when the output's low, boom, it's taking the capacitor, going through that resistor, and bleeding it off to ground. Eventually, that capacitor discharges to the trigger point, the low trigger point of the Schmidt inverter, and because it's a Schmidt inverter, it will instantly trigger with no delay, shifting the output high again, where, again, it goes through this diode, through this smaller resistor, recharges the capacitor, and then boom, the cycle repeats itself. Now the idea here is that we have this blocking diode so that only high passes through the small resistor. That small resistor, this particular circuit, is 470 ohms. So this capacitor is going to charge rapidly, and when it is charging, the beep is let out. So that resistor right there is directly proportional to how long of a beep you want. Then of course, when it switches back low again, it can't go this way, so it's forced to go through the smaller one. And that's where our duty cycle comes in, because that's how we set the duty cycle of a Schmidt inverter. We want a really long low, a really short high. Meanwhile, the only thing that the TC4 can't do that the other logic can, generally these parts have a general general wattage dissipation rating, and the higher voltage you run them at, the lower amperage they can handle. So you can see down here, we got like, you know, output current high, which is what would be driving the beeper. And at around the 10 volt range, well, we're like what, 2.2 milliamps? It doesn't have enough chooch to actually drive the beeper, which could require up to 30 milliamps. So we have to buffer it. And in this particular diagram, I'm showing a transistor. 1K buffer, there's the transistor. It's going to be an NPN type connected to ground, driving the negative of the beeper, which is directly connected to positive. We don't have to worry about pull up or pull down resistors on the transistor because the output of the inverter is active. It will control the transistor either way. And in fact, this isn't what I went with the design. I went with a 2N7000 MOSFET because it simplified it. I actually was able to eliminate that 1K. The MOSFET, unlike a transistor, can be directly controlled. We don't need a buffer. Now, under normal circumstances, it would sound like this. Just a plain beep, and if you like that sound, go for it. But I actually added a little something to the circuit, a 220 UF capacitor on the output of the MOSFET. And what's that look like? Right here. And what does that do? Well, when the beep gets triggered, the capacitor charges up a bit, and then when the transistor disconnects power, well, the capacitor will discharge its remaining power and give it a cute little... And I like that extra little added effect. It really put the icing on this cake. So for the purpose of illustration, I'm going to replace the duty cycle resistor RD with something bigger. We're going to go from 470 ohm to 4.7K, so you can hear the difference it's going to make. See? Longer beep. Let's remove the capacitor. So basically you set RD for how long of a beep you want, and that works directly proportional to the charge capacitor you're going to use. Right now I'm using a 470U. If I change that to a 1200U, then our beep becomes, see? Actually a bit longer, yes, because it's charging the capacitor more. Now, to some capacity, the sky's the limit for what you can do here. I'm using a 470U capacitor on this particular circuit. You could put a 1200U and get twice as much time. You could put a 2200U and get 4 times as much time. 470 is the sweet spot with what I wanted to work with. Now, you might be asking yourself, well, that's an SMD component. How do I work with that? Well, if you can do small soldering, use the BOB00717 adapter. That's my go-to for an SOT23 type part that this is. You don't have to worry about getting too confused because as far as I can tell, this TC4 is only available in SOT23. So if you don't want to work with an SMD component, you just want, bud, give me a freaking jelly bean I can pop right now. Well, then you're gonna look at something like this. What's this? It's an MCP 1406 in a PDIP 8. This right here is what's known as a MOSFET driver. This is a device that allows you to take a logic signal like you might generate with a PWM, either out of your Arduino or out of some basic logic chips, and translates it into a voltage and drive current that will run a MOSFET. If you directly try to run a MOSFET off logic voltage, it might not switch on and off fast enough to get the clock speeds you're going for, so this is the intermediary. However, the wonderful thing about a MOSFET driver is it has MOSFETs in it. So you can pretty much hook it up directly to a load. In the example of this particular guy, it's rated for 6 amps peak. Now you would use these to drive MOSFETs that might have to do like 100 amps. You'd find something like this in say a 3-phase controller to translate what the microcontroller's doing to a signal the MOSFETs want to switch that fast. But if you have lower current capability than what the driver is rated for, you can run stuff directly off of it. We have a MOSFET connected to positive, a MOSFET connected to negative. It's inverting. It has a Schmitt trigger. We can pretty much implement this thing identically to the TC4. Extra added benefit that we don't even need that buffer MOSFET anymore. We can connect the beeper directly to this guy. Now it has separate outputs, which you will tie together. The only thing you need is you replace, say, if you want to use the capacitor, you would need a diode. So on the output of your inverter, you would have a diode proportional to the current direction. In this case, we're running off low. Then we would have our capacitor, which I drew horribly wrong, to the plus, and then that would run our beeper. The reason why is because as soon as this switches, it's going to discharge the capacitor instantly. If you want that mew effect, you need that to block it from discharging. So if that's such a sweet frickin' deal, bud, why am I not using a MOSFET driver? Well, it's got a bigger footprint, and when you see the device that I build, I couldn't make room for it, even though I could eliminate a transistor. The other reason is it's slightly harder to time. You see, the MOSFET driver has a very narrow window of hysteresis. It's not really designed to be used like you would use an inverter. It's not designed to have that hysteresis range. They probably didn't intend you to use it for relaxed oscillation, even though it will do it. And the reason why it has that tiny hysteresis is because it has to respond very quickly to what logic or microcontroller is telling it to do so that it switches those MOSFETs correctly. Now, in order for you to understand that, what hysteresis is, this is going to be, we'll say 9 volts positive. This is going to be 0 volts negative or ground. And in the middle, we have these 2 trigger points. That's the high trigger point, and that's the low trigger point. And remember, this is the input voltage going into the inverter. So, say our inverter is already high on the output, and we have a positive charge going up, going up, going up, going up. Once it hits this high point, that's when the inverter will trigger and put out low. Consequently, in our situation where we are starting high and the capacitor is discharging low, 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 it hits this low point and that's what triggers the change. The hysteresis is the voltage gap here between the high and low point. It could be, up to 2 volts as an example. And in a relaxed oscillator, how the oscillator works is directly proportional to this, because this is basically where our capacitor's riding. We never really reach fully high and we never really reach fully low. The capacitor charges up until it hits the high trigger point, which might only be, we'll just throw a number out, 7 volts, just for the sake of throwing a number out. And then as the capacitor discharges, it might only go down to as low as, say, that might be 2 volts, which these numbers don't add up, but you get the point. The capacitor is just going to be going between these 2 numbers. This might actually be more like 4 volts. So it might only be charging up between 2 and 4 volts as it oscillates. The MOSFET driver is going to have a really much smaller window. Those numbers are going to be way lower so that it can accommodate logic voltages while being able to operate at higher voltages itself. So that might be like 1 volt, and this might be like only 2 volts. So now we only have 1 volt of range. That means it's going to oscillate faster with the same amount of load capacitance. This guy right here. So what happens is if I use the MOSFET driver, I have to go from using a 470 to hit my sweet spot to a 1200, which as you can see, it's bigger, and depending on how much room I have to work with is not good. And indeed, I'm working on tight spaces. I want to fit this entire project into this Hammond box, a 1590A, and still have room for a 9-volt battery that's going to take up most of the space. I actually had to redo this design a couple times to fit in just a sliver of this perf board. And I got it down to what, just 9 lines? Yeah, 9 by 10. That's what I needed to do to be able to fit a battery in there. That MOSFET driver would have taken up more room, even with this thing out of the way. I would have needed a physically larger capacitor. It just wasn't a good time. I decided to stick with this design, and I have the ability to do the SMDs. But if you got a little bit more room to work with, or you know how to do this, maybe you can come up with a different plan. If you omit this switch, you could definitely fit it in there. But that switch is there for a reason, because I want 2 different times. Which brings us to how to time this thing after I take a piss. So we're gonna go ahead, we're gonna start off with something much smaller to set a baseline, like a 10K. And this puffer's gonna start beeping, and then as it beeps, we're gonna time it. I'm getting a lot of 2.56s. So how do we turn that into math we can use? Well, simple. 2.56 seconds divided by a 10K resistor is a multiplier of 0.256. So now let's say, what happens if we want a 100K resistor? Multiply that by 100K equals 25.6 seconds. All right, let's try it. Oh, thanks, Obama. Also, when we kind of have a feeling for when it's going to beep, it's going to make it easier to anticipate said beep. So We're expecting around 25 seconds, even though I started the timer late. Oh, it was at 23 and I delayed. I don't know why the computer has to think right now. 24:01. 24:49. 24:37. So we're pretty much getting sub variation at 24 seconds, which is close enough. And that results in a math of 0.24 and whatever seconds. So now we can predict how much time we want. So say we want 1 hour, 60 minutes times 60 seconds equals 3,600 seconds. Divide that by 0.24 and we have 15 megs, which is why I have been using this circuit with a 15 meg resistor. Now I got nothing between 10 megs and 2.2 megs. How much time will we get out of a 2.2? Well, what I have is a 2210, a 2.21 multiplied by 0.24, and we're gonna get 530 seconds divided by 60 seconds. We're gonna get 8 minutes, 0.84. And if we take away that 8 to isolate 8.4 and multiply that by 60, it's gonna translate it to 50 seconds. 8 minutes, 50 seconds. I have some other resistors on order to more vary this, but you know, we're gonna stick with roughly 10 minutes and roughly 1 hour for now. And that's what this switch is all about. A 2.2 meg for the top, a 15 meg for the bottom. And that is based on my calculations for a 470U capacitor. Now, here's the only other thing to consider, battery voltage. That time is gonna change with battery voltage. I've gotten timing variances anywhere between 0.22 and 0.25, depending on the state of the battery. But you know what? For the purposes of this demonstration, it's not a big enough deal. Either way, every hour, this thing's gonna let out a little mew, and if you've got it hidden around somewhere, someone's gonna be like, did you hear that? Did you hear that? What was that? What is that strange noise I keep hearing? I feel like 8 minutes would be too obvious. 20 to 30 minutes is going to be a target that I'm going to be shooting for. And if we want 30 minutes times 60 seconds, 1800 seconds divided by our math of 24, that's going to be a 7.5 meg resistor, which I have on order so that I can get that timing. And of course, you know, we don't need an audio amplifier. It is just a plain Jane beeper rated for about 12 volts, 2.3K. And in this situation, I'm using the $3.56 CEM1212C. There are cheaper ones. They work just as well. I don't know why I decided I wanted to choose this one. Maybe find one that can handle 9 volts and is more dB than this. 85 dB at 12 volts, 10 centimeters away. I wish it was just a touch louder, but it's gonna be fine. So now, what the fuck was that? So now I wish to build on this thing. Okay. So I need about 9 holes down. We're gonna be cutting her right about here, bud. And these particular perf boards, they're stiff. They are not the easiest things in the world to cut. Measure twice. Just need to saw a little score into it. Probably do that with a sharp blade too. I'll save this scrap for another project, right? As you can see, some of the components are being mounted on the bottom side with the beeper actually being socketable. Because of how I'm going to be mounting it into the box, I figured this was better. That, and I needed a bit of standoff so that it would protrude out of the chassis enough in respect to the switch, because the switch is going to set the depth. And with this right on the board, it was sitting too deep down on there. Now, of course, I made the 2 timing resistors socketable so that I can change them. I just have to throw the TC4 on here, which is going to be tricky now that it's on there. Do you believe it goes upside down like this, huh? Yes, it does. Let's set that aside. Got to get a little bit of Rosman schmoo on there first, sir. Tin it up. Now, can I have a steady hand today, please? Apparently not. I should have mounted this before I put it down. All right. Now I just have to clean up. Where's my alcohol? Spritz, spritz, spritz. Brush, brush, brush. Spritz, brush, brush. Brush, brush, brush. Aha, that's a clean chippy. So let's, as an example, we'll take a 10K resistor, chuck her in there. Flick the power towards that. Get a 9 volt ready. Negative is going to be, I made a tight path to get to negative, didn't I? Did I ever? Well, jam a wire in there and then touch a wire to where the positive's gonna connect. Oh, that's a 1.2K actually. She's gonna work. Now it's just a case of fabrication, bud. How do we get this into there with enough room for the battery? Oh, it's got to be a tight fit. So if you're feeling a bit left out because I didn't show you the full perf boarding process, well, welcome to the channel. I have other videos of me perf boarding. That's part of the incentive here, right? You're gonna follow the channel, aren't you? Also, what I am gonna show is the assembly. Because our tolerances are rather tight here, we have to be careful that we give enough space for the battery, which means we need this as forward as possible. Now I cut a little bit of relief on the board here so that could be possible. And now I essentially have to line this all up. And it lines up right about here. Got a bust out trusty combination square here. I'm gonna copy that line all along the front. So our board's gonna sit right about there. So now let's see if we can figure out where the switch is gonna be. I should copy it on this side too. All right, switch would thereby go tilt down, oh, come on now. This switch, by the way, is an eSwitch MDP3. That is 200 series mini toggles. It's very important because the 100 series mini toggles won't line up with a perf board. MDP3 means it's a DP-DT switch with the on-off-on configuration. The rest of the part number is a T2. That's the paddle. I wanted the smallest one possible. T1 is much longer, sticks out more. I want it to be low profile. Then there's B1. That's the bushing. You have to watch out when you're looking for the part numbers for these switches because they come in threaded and non-threaded. So don't get a B2. And then we have M2. That's next. That has the PC pins to mount them to a board. M1 would be little solder lugs. Following that, we have RE. That has to do with the contact plating material. And then there's a final one, an H. That means it comes with hardware. They didn't have in stock at the time of buying this the H version, so it ends up being 200 MDP3 T2 B1 M2 RE. No H at the end. So if you order one of these, you also have to get an HDW21 and an HDW22. That's going to be the nut and the lock washer. I don't bother with the outer washer because I don't like it's big and it has that little hooky thing you just have to break off. I just go to the hardware store, get some stainless number 10 washers, and boom, call it a day. All right, so our switch hole is on this line here. So now we kind of put the switch on like this, lining up the board as well as we can. And we mark right the center point. So right here on this X is where our switch is going. I'm gonna call in a consultant and pew. Okay. Now I gotta figure out where this beeper is gonna go. It's gonna be a little bit more tricky. Set it up from this side. Right here it looks like. Copy that across, and that's going to be slightly offset from the switch itself. So we're going to line it up like this. We're going to look at the center right there. Oh, okay. Does that make sense? Uh-oh, no it doesn't. No, we're off. Measure twice, right? You know, the quickest way to do this is the switch is right center on this set of perfs, and then the beeper would be on this perf line. How did I get it so far off? Okay, well, we figured out the correct reference just in the nick of time. I'm confident about that center point. Pew. Two holes to freedom. Except to determine the size of this hole, we have to force it through its grommet that we're going to be using. And the fact that it's so hard to get it through this grommet is one reason why I chose to do it socketable. It's going to flex that grommet wider. All right, what size hole do we need for grommet? Look at about 14.21 mil. Again, we're using cone bit for this one. 14.2 is 9/16, so we'll start with 9/16 and work our way up. Let's go back to the 80s and fire up old Pressy boy here. Remember, you cannot you can't impress her if you don't chamfer and deburr. Beepy goes through. That's 12. We need to go another step. That's our 14.25. Oh, we got a little bit of tolerances in there that worked in our favor. I'm pretty sure I got this thick enough to fit this hole. It looks a lot tighter now that it's in there. Let's see if we can squish the beeper through, just so we're not here all day. Oh boy, she's jumpy. I might have to grease the beep. Grease the beep. Okay, well, this is not working in our favor. Okay, here's what I'm gonna do. I'm gonna drill the hole that I need to mount the switch. Make sure everything properly lines up before we get too into it. So now if we mock fit this, do those beeper holes even line up? Uh-oh, that's what I was afraid of. I knew something would be problem. It's almost like my initial line was the correct line. Wow. This is the part of the process that I'm not that good at. Yeah, it's too high. It's funny how that works. I don't think these things will go mill sideways, will they? At least now with this hole elongated, which I did manage to elongate it some, we have a better chance of fitting the beep. We're gonna end up with a big sloppy hole. Okay, now it's just a case of fitting this grommet into this hole some way, somehow. You'll forgive me if I expedite and edit some of this out. Can we just force it down? I think we're getting it. It's starting to look promising. And it's not completely chowdered on the other side. Just as good. All right, that's quite possibly not coming out of there anytime soon, but that's part of the desired effect. We just need to rotate this and hope that when we install the PC board, those pins are gonna line up. Come on, bud. And they do. Okay, we're almost done, buds. We're almost done. Once this fits together, we're gonna put a little bit of glue to keep that beeper where we put it. All right, so let's get our hardware mounted again to confirm fit. So, just wrench that into place, bud. Okay, so we didn't get as tight to the front as I wanted. So now is the battery still gonna fit in here? The idea is the battery's gonna cut. Oh yeah, it'll be fine, bud. All right, let's get the battery soldered on. Let's also get some test resistors into place. So 15 meg is gonna live in this bottom position. So we'll go ahead and trim that to fit right away. In the top position, I was gonna put a 2.2 meg. I'm gonna put a 10K in here for now so we can test it once it gets working. Just fold that over nicely. Shouldn't get in the way. All right, time for the peel. Okay, we should have power now. All right, let's get this finally installed. We're actually confirming fit of the beeper. Do we have glue yet? Some good old-fashioned hot snot. Stop that pupper from moving on us. That'll do. Now let's get it installed. All right, so if I pop a battery on now and flick it to the down position, it's working. So let's pull the 10K out. We'll put our 2.2 meg in. I'm gonna be waiting for something more like a 7.5 meg. So I'm not gonna cut this one because it'll get repurposed one day. Our battery probably should have used some glue on the other side. It'll just slop in there like that. Now I put a cover on it. Ooh, you know what we should do? I gotta stuff a bit of foamy on the arse ender here. So it doesn't, yeah, it's pretty good. Where's the screws? Ho, 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 ho. It's the satisfying thing when you can finally put the screws in. And know that you don't need to be opening it up again anytime soon. Other than to, if I actually leave this somewhere, well, I'm gonna probably want to put a disposable battery in it. According to my measurements, I believe this guy used somewhere between 150 to 200 microamps. Either way, my math says that this thing should be able to run for almost 2 weeks. Or, you know, I've tested this circuit to a solid week. It ran down the battery pretty good after a solid week, but still, you could put this somewhere and it's gonna be running for a week. And that is with a rechargeable. Chances are you're gonna stick a disposable on there and you're easily gonna get double that. So that is one disadvantage over the Arduino solution. The Arduino goes to sleep mode and your battery's gonna last years in that one. This one being mechanical, it is going to consume power to do nothing. It is going to be using power while it's waiting for the next event. But at the end of the day, it is simple, it is easy. You could build one yourself and it looks cute and it sounds cute and it is ready to prank someone. The question is, can I come up with prank footage? I don't know. And one of the ideas with the Switch, the long game setting is at the top so that if someone kind of just like turns it off, assuming they just flick it all the way down, they don't realize that they've left it on and it's actually going to go to the 10-minute count. So they're gonna get some more beep out of it. To actually turn it off would be center position. But we're gonna put it on lower position now. We're gonna wait for a little bit of beep just to confirm it's working. And then I think that is just about it. I hope you enjoyed this. If you did, stay tuned because I like to build little interesting projects. I got some other little interesting perf-boardy type projects coming up. So yeah. Again, don't know how to end these videos. Thumbs up this time. Subliminal message it is. You know you want to.